Hello everyone, I welcome you all to the course of heat transfer. In today's session, we will discuss a topic called as heat exchangers. Basically, heat exchanger is a device wherein the two fluids which are at different temperatures exchange heat between them. There are many applications of heat exchangers. It could be radiators, it could be refrigeration system, it could be air preheaters, it could be condensers, it could be economizers, it could be heat recovery as well as chemical processing units, food processing units, etc. Now, if you see the mode of heat transfer in heat exchanger is mainly out of convection as well as conduction. Now here we will come across a term called overall heat transfer coefficient, which will contribute to the effects of conduction as well as convection. Now we will also encounter a term called LMPD, that is logarithmic mean temperature difference. It is nothing but that equivalent temperature difference between the two fluids for the entire length of the heat exchange. It means if you consider a heat exchanger, along the length of the heat exchanger, the temperature keeps on varying. Now, if you take the temperature difference between cold fluid as well as hot fluid, which is equivalent to the logarithmic mean temperature difference, the amount of heat transfer will be as same as that of the actual condition. Hence, we will be using the logarithmic mean temperature difference in calculation part of the heat exchangers. Next, we have classification. We can classify heat exchangers based on the processes as direct type as well as indirect type. In direct contact type, as the name itself indicates, the two fluids will contact directly. Example could be your cooling towers, jet condensers, as well as superheaters, where the hot fluid as well as cold fluid come into contact directly. Let us see an example. Now here is a cooling tower, schematic diagram of a cooling tower. Now if you see, there are two fluids. One is air, which is flowing from the bottom, and another is a water, which is made to sprinkle from certain height from the base. Now, the water is at elevated temperature. Your intention is to reduce the temperature of this water by heat transfer. Now, how to do this? Now, water droplets are made to fall in the stream of air which is flowing from the bottom. Now, this stream of air will catch the heat which is given out from the water particle. This water particle loses heat and it will be collected at the bottom. So this can be used again for further uses. It could be in power plants. Now, if you see here, there is a direct contact between a hot fluid, which is water, with a cold fluid, which is air. Now, air rises up by catching the heat, and the water will drop down by giving out the heat. Next type of classification is indirect type. In that, the first one is recuperators. In recuperators, the cold fluid as well as hot fluid flow simultaneously, separated by a wall. Many of the heat exchangers are generally a recuperative type of heat exchangers. Now, another type is regenerative type of heat exchanger, wherein the cold fluid as well as hot fluid flows alternatively on the same surface. I mean to say, let us consider a matrix or a heap of pebbles which acts as a matrix. Now, over the heap of pebbles, first I will pass hot gas. The energy from the hot gas will be transferred to the pebbles, which acts as an energy storage device. After a certain retention time, the hot fluid flows out, but the energy is absorbed by the heap of pebbles. Once the hot fluid flows out, I will allow cold fluid, let us consider it to be water. Now, when I pass water on the heap of pebbles, again there is temperature difference, and this time the pebbles will give out heat to the water. Of course, there is heat transfer between hot gas as well as water, but it is not a direct type of contact, but using some matrix. In this case, it is pebbles. Using this pebbles, the heat is made to transfer. If you see, the hot fluid flows first, then the cold fluid is made to flow. In such cases, the hot fluid as well as cold fluid flows alternatively on the same surface, which is called as matrix or energy reservoir. If you see the figure, you'll understand. Now let us consider this diagram. Now if you see here, we have hot fluid as well as cold fluid, inlet as well as outlet. Let us first consider valve A is open, valve B, C as well as D is closed. Now when hot fluid comes, it will come in contact with this matrix. Then valve B is opened so that whatever fluid was there inside the matrix will flow out. Now the valve A as well as valve B both are closed. Next we will open valve C, which is a cold fluid. Now this cold fluid will flow into the matrix. Here the matrix will give out the heat that has been absorbed in the previous flow of hot fluid to the cold fluid. Once the heat exchange has occurred, we will close the valve C, then we will open the valve D. Now obviously the cold fluid has gained some heat and it will leave the heat exchanger with elevated temperature, whereas the hot fluid has given heat to the matrix and it will leave out the heat exchanger with a lower temperature. Similar is the case for rotary generators. Next type of classification is according to constructional features. The first type is tubular heat exchanger. You can see there are two concentric tubes. One is carrying fluid B, another is carrying fluid A. This type of heat exchangers are called as tubular heat exchangers. Now if you see, the fluid A is moving from left to right, fluid B is also moving from left to right. If both the fluids are moving in the same direction, then we call this as parallel flow. Next, suppose fluid B is moving from left to right, whereas fluid A is moving from right to left, then they are opposite to each other. Fluid B is moving opposite to the direction of fluid A. Then we call this as counterflow heat exchanger. Next type of heat exchanger is shell and tube, wherein we have a shell which is enclosed with a number of tubes. You can see in the diagram. Now this is the shell and these are the tubes. If you see here, let us consider inside the tube we are passing hot gases and in the shell we are passing cold water. There are two fluids, one is hot gas and the one is cold water. Now the heat has to transfer between these two fluids. If you consider, this is the tube inlet, which is hot gas. Now this will enter and flows along the tubes. There are n number of tubes of such kind. In the cross section we can see there are 4 tubes, but there could be n number of tubes of such kind. Now from the tube inlet we are passing the hot gas, which is at elevated temperature. Now from the shell side we are passing a cold water. If you see, the cold water is made to pass over the surface of the hot tubes and it follows the path as directed. It will follow this way and exits at this end. Now if you see here, we have mounted some metallic strips to the inner wall of the shell. They are called as baffles. These baffles are used in order to increase the turbulence, which in turn increases the retention time. It means the time of contact between the cold fluid as well as hot fluid will be more. As a result, it will increase heat transfer. These are some more examples. This is one shell pass and two tube pass heat exchanger. This is the shell. One is black and the tube is as shown. If you see this, this is two shell pass and 4 tube. It means we are passing once, we are passing twice. So this is 2 shell pass and 4 tube. This is 1 shell pass and 2 tube heat exchanger. The next type of heat exchanger is fin type. We have already discussed a fin is nothing but an extended surface which is used to enhance the heat transfer. You can see fin type of heat exchangers in automobile, air conditioning system, cryogenics, refrigeration system, airplanes, etc. Next type of heat exchanger is compact heat exchanger. As the name itself indicates, compact means which consumes less volume, and it is determined by a term called area density, which is defined as the ratio of surface area to unit volume. Now, if a heat exchanger with the area density greater than 700 per meter, then we call that heat exchanger as compact heat exchanger. The area density of a particular heat exchanger, if it is greater than 700 per meter, then we can categorize that to be as compact heat exchanger. Nowadays, compact heat exchangers are getting importance in automobile sectors, particularly for radiators. Next, according to the flow arrangement, as we have discussed earlier, parallel flow as well as counter flow. In case of parallel flow, the hot fluid as well as cold fluid moves in the same direction. If you see, the hot fluid is moving in this direction or from left to right, the cold fluid is also moving from left to right. So this type of arrangement can be considered as parallel flow. On the other side, the hot fluid is moving from left to right, whereas the cold fluid is moving from right to left. Both the fluids are moving in a direction opposite to each other. This can be considered as counterflow heat exchanger. One more type of flow could be cross-flow heat exchanger, wherein the two fluids meet in transverse direction. If we see the diagram, I'm sorry, in cross-flow heat exchanger, if you consider the radiators, radiators are nothing but cross-flow heat exchanger. This is the diagram. You can see the hot fluid or fluid A is flowing through the tubes and fluid B is meeting the fluid A in transverse direction. Fluid A is moving along the axis of the tubes, whereas fluid B is meeting fluid A in transverse direction. Again, there could be both fluid unmixed as well as one fluid mixed and another fluid unmixed. The difference is that when we say both fluids unmixed, this stream is entirely different from this stream. There should not be a cross flow of fluid B with another channel. Whereas if you see here, the fluid which is flowing over the tubes can flow in any direction. So this is a mixed. So here fluid B is mixed, whereas fluid A is unmixed. Hence, one fluid is mixed and another fluid is unmixed. Next, we will consider a concept called as fouling factor. Fouling is nothing but material deposition over the surface of the heat exchange. It can also be called as scaling, whereas some salts or some deposits will be occurring on the surface of the heat exchanger. To give you an example, if you consider a water heating coil, after certain period of usage, if you see the surface, you can find it is adhered with some deposition over the surface. That deposition is nothing but fouling. Now this acts as a resistance for the heat transfer. The fouling in turn increases the resistance, which will decrease the heat transfer. Fouling need not be a disadvantage all the time. If we need to store the energy or if we want to reduce the heat transfer, the fouling can be in support to the phenomena or the process. So which can be seen in the applications like refrigerators. We have corrosion fouling, we have chemical fouling. You can see the salts like CaCO3, CaSO4, MgOH twice, MgSiO3 will get adhered to the surface of the heat exchange. With this, we'll stop here. In next class, we will consider the derivation part of LMPD, both for parallel as well as counterflow heat exchange. Thank you.